Hi everyone, welcome to my channel. On this channel I talk about system design, lead code and general conversation about career and life. I'm starting a new series on system design and this is my very first video. I'll just basically give you an introduction of what actually system design is and what are the things to consider when we are designing a system and what do we really mean by designing a system. Every system has two components, a client and a server. So the client sends a request to the server and the server sends a response to the client. Now this response client can be, let's say, web browser on our computer, and this response might be some HTML web page, and this server is some server which is publicly accessible over the internet using some public IP, and we send this request to fetch this particular web page. Now what system design includes is things like what kind of web server do we want to use. So what should be the size of that server, size in terms of what should be the RAM of that server, what should be the hard disk, or if you are using SSD, what should be the size of the hard disk or the capacity of the persistent storage of the server, what should be the CPU of the server, does server needs any GPUs, and all those kind of things. Do we need one server or do we need multiple servers? So based on our requirements, based on the type of website, web application or mobile application or whatever system we are building, the answer might be different. And in system design interviews there is often a no single right answer. There are always trade-offs. If you use one over another, you are doing that based on some of the assumptions on how the website or the system will be used. Other considerations are what kind of database will you use. The most popular databases we all know are relational databases, basically MySQL, Postgres, all these are relational databases, and usually it uses structured query language to kind of query these databases, and these are the databases which are relational, which means that it stores the data in form of rows and columns in forms of tables like an Excel sheet, and then you can perform joins on these databases. Then there are non-relational databases. All these are non-relational databases, and non-relational databases typically don't support joins. The advantages of non-relational databases is, let's say you want applications where you want low latencies. In those cases non-relational databases are useful, or the storage space is humongous. For example, in kind of social media applications like Instagram and Facebook, where we want very low latencies and we have lots of data in forms of images and text. Also, like if you have unstructured data, like I mentioned, images and text, then we use non-relational databases. I think one of the type of database I forgot is to mention here is blob storage. I'll just write it here, and let me briefly go through each of these kind of databases. So relational, we all know, it's just like an Excel sheet. Key value stores is the kind of database where you just it's a persistent hash map. You have a key, you have a database, you say okay, store this key 1 with this value 1, and then you can query this database, okay, give me the value corresponding to this key. That's basically key value database or key value store. And then we have column stores, and in column stores, the difference between key value stores and column stores is that column store supports composite keys. For example, let's say we have column 1, which is the primary key, let's say. So key value stores only support this. But let's say we have column 2. Columnar stores can basically combine these columns to query the data, and usually it provides some kind of sort key. So example of key value stores and columnar database are DynamoDB, AWS DynamoDB, or Cassandra. And based on how you use them, you can use it like a key value store or a column store. So in a columnar store, the primary key can be repeated. 2 rows can have same primary key. For example, let's say the primary key is, let's say, state, for example New York, and then within that state, let's say we have different cities, and those cities are sorted by their names. So city 1, city 2, all these cities belong to New York, and these will be sorted by their names, and that's why we call it sort key. And the combination of primary key and sort key is usually unique. And we'll go into more details of these column stores and how and why they are useful. But for now, you can say that column stores are kind of key value stores where key consists of a primary key and some kind of sort key. Then we have graph stores, and graph stores is basically when we want to store social network kind of data, where we have nodes and we have links between them. Like let's say node A is a friend of node B, or node A kind of follows node B, where it is not a two-way link, it is a one-way link. Node A follows node B. And graph databases are kind of optimized to store such kind of information to make any queries. By optimization, I mean if you want to query, let's say, give me all the friends of node A, it will be very fast in graph database. You can also store this information in a relational database or maybe in a key value store. But why we have specialized database for special use cases? Because for those use cases, when we will write a query on a graph database, it will be super fast. And that's why we have so many different kinds of databases. Ideally, you can store any information in any database, but they would not be highly optimized for that particular use case. And finally, we have document stores. A typical example of document store is MongoDB. You can consider a document to be simply a JSON document or an XML document, where you have information like, okay, name, city, and then marks, and you can have nesting inside it, marks in English subject, let's say 25, and then maths, let's say 50, so something like that. So it's just basically a nested form of data structure where you have, and this is document 1, and you can have multiple documents. So basically advantage is you don't already need to know, okay, what would be the fields corresponding to a particular document. Like some of the documents might not contain marks, some of the documents might contain extra information. So when you want that flexibility, you can use document stores in relational database or in key value store or column stores, you usually need to know what kind of columns would be in the database beforehand. Although the document stores provide this flexibility, it does not provide other kind of advantages which relational database or key value store provide in terms of faster queries for specific use cases. So there are different various kind of trade-offs which we might go into depth in a later video, but for now I think this high level understanding should be good enough. Now moving to caching. So if you don't know what caching is some kind of a temporary storage which is usually faster than a original database or a so this is a persistent storage. Once you store the database, it should ideally persist forever until you explicitly delete it. Caching is a temporary storage. Data may not persist in this kind of storage. The only idea of caching is why we still use caching is to fasten the process, to fasten the queries, and that's why it's typically faster than a database. So it's always faster than a database. That's the purpose of caching. So oftentimes caches are in-memory databases, like in-memory databases. So the data is stored in memory. Typical examples are memcache, Redis. All these are some examples of in-memory databases. And the advantage is that the data which is used or read again and again, like frequently accessed data, can be retrieved very fast. So typically you can create a system where let's say this is the client, it needs some data, it goes to the cache server which stores cache data, it checks whether that data is available in the cache server or not. If it gets the data from cache server, well and good, otherwise it queries the original persistent storage database. So a lot of times, let's say if 80% of the times it gets the data from the cache, and let's say cache takes X amount of time, and getting the data from database takes, let's say, 10x amount of time, then effective time to get a query is 80% times x, and rest 10% of the times 11x, because it has to query both the cache and the database. Sorry, 20% of 11x, which is equal to 3x. So effectively the overall time to make a query has been reduced from 10x to 3x if we use caching. So if we use cache, then we have different kind of considerations to make. How long will the data stay in cache? So let's say we can say after 1 minute the data will be expired in the cache and it can be safely removed from the cache. Consistency means the cache and the original database should be in sync. Otherwise, if we have old or stale data in the cache, it might give us wrong results, and that might or might not be acceptable depending on our use case. So we might need to keep them in sync, and it depends on like what kind of use case we have and how frequently we need to sync it, and what kind of consistency level we want. Eviction policy means that, let's say if we want to store a new entry in cache and cache is already full, then which entry will we remove from the cache? And there are like multiple strategies by which we decide which entry should we remove in such a case if cache is full. So that's called eviction policy. So we'll talk about all these things when I'll create a video on caching. For now, let's move on to the other considerations in the system design. So what do we mean by scalability? Let's say you were getting 100 requests per second, and suddenly your website became very famous and it started getting 1,000 requests per second. And let's say after after some time it became even more famous and it started getting 10,000 requests per second. So scalability means as the amount of workload increases on your server, how do you handle it? So there are two ways you can deal with it: vertical scalability and horizontal scalability. Vertical scalability means, like, let's say you had a server and it had 10 GB of RAM and let's say 1 TB of hard disk. Now vertical scalability means, let's say you increase the RAM from 10 GB to let's say 100 GB. You increase the hard disk from 1 TB to let's say 10 TBs. So vertical scalability means you keep on increasing the capabilities of the current server. But problem with this is there is a limit to which you can increase the capacity, because beyond that increasing the capacity would be super expensive. Like if you try to increase the RAM or the hard disk beyond a certain point, it will cost you a lot. Another thing is, let's say if you have just one server and if that server goes bad, on which you have already spent a lots of money to increase its capacity, and that server kind of dies down, then you are not able to take any more requests. Your system kind of fails and the website will go down, and we do not want any single point of failure. So oftentimes in modern systems we use horizontal scalability instead of vertical scalability. And by horizontal scalability means, if we have one computer with 10 GB RAM and 1 TB hard disk, and let's say server 1, let's say if the demand increases, we'll add more servers. We'll add server 2 with similar capacity. Whenever a request will come, we will send that request sometimes to server 1, sometimes to server 2, and that's why the load is kind of distributed. And effectively, basically your requests are being served from both the servers. And the good advantage is, even if one server goes down temporarily, you can still serve the requests from the other server. And even if it goes down permanently, you can create a new server in the meanwhile, so that you still have kind of two servers, and you can keep on adding more and more servers depending on how many requests you are getting, what is your requirements and all. It ends up being cheaper than vertical scaling eventually. You can also auto scale. For example, let's say during daytime you get higher requests and during night time you get lower requests per second. So you can add more servers during daytime. You can write a code to add more servers, spin up more servers during the daytime automatically to be able to handle large number of requests. And during night time you can write a code to kind of deprovision those servers or remove those servers from the system. And that's how it costs cheaper, because when your capacity is not being used, you are using lesser number of servers, and to run lesser number of servers, it costs better. And for horizontal scaling, you need some kind of a load balancer. Load balancer is a server. It's a web server which basically decides which server to send the request to. So let's talk more about the load balancer now. So load balancer is a server whose IP address is public. This is our load balancer. It has a public IP address, which means anyone on internet can detect a load balancer. The client, let's say our web browser, would go to the load balancer, and load balancer will determine, okay, we have multiple servers here, server 1, server 2, server 3, server 4. Load balancer will determine which server should it send the request to, and all these servers are not usually accessible from the internet. They are only accessible from a local network. They have a private IP address, so you cannot access these servers from internet. Only load balancer, which resides on the same local network as these servers, can access these servers. Now the question you need to decide as part of system design is, what is the strategy of the load balancer to kind of distribute the load between the servers. There can be multiple strategies. For example, one of the strategy can be for all the, you maintain a kind of a table in this. You maintain a fixed strategy. Let's say you have a hash map inside this, which says, okay, let's say all the people whose name starts with A would go to server 1, all the people whose name starts with B will go to server C, and let's say we have 26 servers, all the people whose name starts with Z will go to server number 26. So this is a logic where you have predetermined, okay, which request will go to which server. And when you have predetermined which request will go to which server, we called it sticky sessions. Sticky sessions means whenever a particular user would call ask load balancer, okay, which server should I access, it will always give the same answer. So these servers can be stateful and stateless. Stateful servers are the servers which have their own database. Let's say server 1 has its database 1, 2 has database 2, 3 has database 3, 4 has database 4. Now let's say a person named Aditya asks the load balancer, which server should I go? It will say go to server 1. Because its name starts with A, it will go to server 1. Server 1 will go to database 1 and store information of Aditya. So when Aditya will again come to load balancer, it will ask back its information. It will again send it to server 1, and then server 1 will query database 1 and give its data to Aditya. The problem with this approach is, let's say Elon Musk came and he says, my name is Alpha. Now Alpha is not in our servers, so the problem is, where do we store this information? We'll need to create a new server, or we will need to assign it to one of the existing servers. Let's say we say, okay, all the people with names starting from Alpha will assign to server 1. Now let's say due to some network failure, server 1 goes down and load balancer is not able to accessible server 1. In that case, if Aditya or Alpha comes and asks load balancer, give us our data, the data is kind of not available because server 1 had its own database db1, and since server 1 is down, it cannot access its own database db1, and that's why we cannot basically get the data, and the system is kind of down for all the people starting with A or Alpha. One of the ways to prevent this is to kind of have a backup server for each, corresponding to each server, one backup which has kind of the data copied for server 1, and this is called as redundancy or replication. That's one of the solutions to this. But in general, sticky sessions or stateful sessions are not a good approach, because let's say due to any reason, let's say the number of people whose name starts with A or alpha are far more than number of people who starts with B. In that case, server 2 would be rarely used and server 1 would be overly used. And the whole idea of load balancer was to basically balance load between the servers equally, and this is called as unequal load balancing. And if we have stateful servers, it's very difficult to add or delete servers in the system and still keep their load balanced or equal load balanced, because because one server might be overwhelmed, other server might not be used as much, and that's why stateful servers are not typically used in the system nowadays. So instead we use stateless servers, and by stateless server means that the servers do not have their own databases. They kind of do not store the state of the request. They do not care where the request is coming from, whether it's from Aditya or from someone else, because they use a common space or shared storage. So all of them will use a common database, and now it doesn't matter, like all the data from A to Z is stored in this particular database. Now the load balancer can use other strategies. For example, it can use pick up a server randomly from one of the servers, because it doesn't matter. Even if A goes to server 3, server 3 will fetch the data of A from this shared database and give back to the load balancer. So it can do random assignment, it can do smart assignment, it can maybe keep track, okay, server 1 is right now busy or kind of overloaded, so let me not send request to server 1. It can somehow keep track of the number of requests sent by to server 1 and number of responses received from server 1, and based on that it can calculate which server is busy, so it can be smart and send requests to less busy servers. Or let's say if it knows, let's say you added a new server to the system because load was increasing, and this server is newer server and it has higher capacity, or it has better CPU, it is more powerful basically, and you can give that information to the load balancer, and then load balancer can smartly send more requests to a more powerful server. So all these things can be done in case of stateless load balancing, and typically in modern day systems we always use stateless load balancing. Usually our servers do not store state. Coming back to replication, I briefly mentioned previously that we cannot rely on one database to store our data, because let's say if database gets corrupted or the database goes down due to network failure, then we need a backup, and that's why we need to copy the data in 2 places and not just one. So let's say this is database 1. Now usually what happens is, a lot of times we have fewer writes and lots of reads, and by that I mean that, for example we use Instagram, right? So we see a lot of reels or posts. So let's say I see 100 reels or posts per day, and I might just post one post per day, create a reel or create a or post an image on the Instagram, that might be just one per day. So the reads are often very large compared to the writes, and that's why whenever we do data replication, oftentimes we have one master database and then we have few slave databases, database 2. So let's say a client, which is our Instagram app on our phone, whenever it tries to write to the database, it will always go to the master database to write stuff. So master database will store the data inside it, and then it will also ask slaves to copy this data just in case I die or something happens to me. Data should not be lost, data should be available to you. So it will give let's say image 1, it will give image 1 to database, it will ask database 2 to store image 1, and it will also ask database 3 to store image 1. Now let's say my friends are seeing their feed and they would see this image, they have to read this image. So this is friend 1, friend 2, friend 3, friend 4. So all the read requests usually goes to slaves, and usually we have multiple slaves and more slaves than masters. And if we have multiple slaves and all of them have our latest image, then they can go to any of these slave databases to get image 1 basically. So this is the master and slave paradigm when we want to replicate the data, which is followed in a lot of cases in a lot of systems. But there are other systems as well, depending on, let's say, in some of the use cases there might be a lot of writes, and that's why our master database can get overwhelmed because there are a lot of writes. So there are systems where there are multiple databases, let's say 5 databases, and there is no master, there is no slave. So there is a coordinator node, coordinator server. So basically it kind of is a load balancer, you can say. So whenever I request some data, either read request or a write request, so the coordinator will assign some server from this randomly. Let's say it picks server 2. Now server 2 will talk to its peers. It's called peer-to-peer network. So basically server 2 keeps on talking to its peers, like all other servers or all other databases, and it has somehow information of, okay, where is this image 1 stored. Let's say it says, okay, give me image 1. So server 2 has information of which server has image 1 stored. Let's say it says server 4. So then server 2 will ask server 4, okay, give back image 1, and then basically 4 will give image 1 back to 2, and then 2 will return to the coordinator server. So in this case there is no master, and Cassandra is one such database which uses this design philosophy. And again, what kind of design we are using depends on the type of use case, the type of data we want to store, and whether it's gonna be read heavy system, write heavy system, or how much latencies are acceptable, and all those kind of things. We'll talk more about replication in detail in one of the later videos. Now finally, one of the things to consider in distributed systems. Distributed systems means where there are like multiple servers serving the requests or multiple servers storing the data. One of the typical problems that we get is, let's say you have people in India and people in US, and then we have some data center in India which kind of has all the data of Indian customers or the Indian users, and then we have data center of US which has all the data of US customers or users. Data center India and data center US. So basically we have multiple data centers because um, let's say a customer in India uh, goes to our service to ask, okay, give me this data or store this data for me. It's faster if it gets connected to this server. So the domain name resolution service is a service which gives the basically IP address of the server, and once we get the IP address, it will go to the server to store the data or to read the data. And if the person is in India and if it goes to the server which is located in India, the latency would be low, but if it goes to the server located in the US, the latency will be high. So that's why we store the data across in the data center which is like closest to that person, and that person is usually routed to the closest data center, and it's called GeoDNS. GeoDNS means uh, resolving the domain name based on the current location of the user, geographical location of the user, so that latencies are low. Now let's say this person is traveling to US for a week due to some business trip. Now based on this person's location, if we again reach to DNS server, it will say, okay, now you are in US, you should get IP address of USA, so connect to the US server. Now this person will connect to this server, but all the data of this person was in India server. So what do we do in that case? That's why whenever we store data of this person in India server, we also asynchronously copy that data to US server. And this asynchronous copying means that we will say to user, okay, we have stored your data, but we only store it in India server, and later on we kind of copy it to the US server asynchronously. So even if this user goes to US server, he will be able to find that data in the US servers as well. So it's called async replication of the data. A lot of these async processes, like this copying of data from India server to US server, are happened using message queues. So what message queues is basically, or let's say you store some data in India server, let's say image1. Now what do you say is you insert this message in a queue, that let's say this is a queue, copy image1 to US server. Now whenever US server is free and can handle some load, it will go to this queue, it will pull out instructions from this queue, and then will execute it. It will copy the image1 from this database. And since the messages are lying in the queue, US server does not have to do it immediately. It can do it as per its own convenience. It's like when your mom says you to do something and you say, okay, I'll do it whenever I'll be free. Just write whatever you want me to do on the whiteboard, and then you go to the whiteboard, you look at all the things that needs to be done, and then you do it as per your own convenience, and that's called decoupling. So basically asynchronously things happen, and that's why we use a queue data structure. This queue data structure is typically the kind of data structure you have heard, where it says first in first out. Basically whoever goes first inside the queue So this is the first member in the queue, this is the second member in the queue, this is the third member in the queue, and this is the front of the queue, this is the back of the queue. So whichever message goes first will go out of the queue, and this is the door. So basically keep on getting messages. Let's say every person is holding some message one by one, and process those messages. That's how decoupling is achieved. So I hope you got an idea of different kind of things which goes under designing a system, and trust me, this is like very high level introduction of things which go very detailed and deep when we talk about system design, and I will be talking about those things in subsequent videos. I hope you like this video. Let me know in comments if you have any feedback for me. Until then, stay tuned. Please subscribe my channel if you haven't already. See you. Bye bye.